Okay, so we've defined Young's modulus as the ratio of stress to strain. We defined stress, we've defined strain, and now we want to just consider how much energy it takes if we have a wire at its fundamental length, its unstretched length, and stretch it with a tension T. So we've got a wire, let the length be L naught, ACS be the cross-sectional area, and let Young's modulus be E. Then we stretch with a tension T. How much change in potential energy? Okay, so what's a change in potential energy? Now I wrote something down here with very little thought, and it was wrong, and it led me to some confusion down here. So let's correct that. Okay, where I had E here, Young's modulus, remember that when we had our proportionality over here, K was the multiplier of this TL naught over ACS that we have here. But of course then, when we put the thing into the form of strain and stress, okay, we found that we had a 1 over K between the strain and the stress, and the 1 over K was the Young's modulus, meaning the Young's modulus would be the reciprocal of the K that we had here, and I just plain old neglected to acknowledge that. So what we have here should be 1 over E. Now this is just your basic Young's modulus relationship. So let's say that the length goes from L naught to L naught plus delta L, where delta L is easily calculated as so. So if we know what tension it is, we can calculate the change in L. And let X now stand for the length, and X is a variable, and X is going to be the length as we stretch it. Because we start at length L naught, we stretch it to length L naught plus delta L. Then delta L can be written as a function of X as just X minus L naught, where delta L of X now is not your total delta L. That would be delta L of, well, okay, I'm just going to write delta L of X is X minus X naught. Okay, then the tension at length X is your delta L of X over L naught times your cross-sectional area over Young's modulus. And this simply by rearranging this relationship. It's the stress, the strain at length X, well, times this. Now, this is wrong because I rearranged this incorrectly, so now I have to do a little correction. The cross-sectional area and E are both in the denominator here. So when we solve for T of X, we get cross-sectional area times E. And over here, going to be the same thing, cross-sectional area multiplied by Young's modulus. Incidentally, the E kind of stands for elastic. It's like elastic modulus. So all these E's I've got here should go up here with the cross-sectional area. So I'm going to make that correction throughout. I'm going to put my E here. I'm going to put an E here. There's got to be an E here, and I think I've got them right now. Again, just because E is the reciprocal of the K I had here. Okay, now, let's look at this relationship for a minute. It makes more sense now, makes good sense, because if you have a greater Young's modulus, that means you have a greater ratio of stress to strain, more force per unit area for a given amount of strain. Okay, that's the relationship that you would expect for a stiffer spring or a stiffer rubber band. Okay, so it makes a lot of sense, of course, then, that if you have a stiffer rubber band, you're going to get less delta L if E is bigger. E being in the denominator means if it's bigger, you're going to get less of this. Okay, so you want to sort that out. You want to think about that as you're working problems. So your delta L of x, again, being defined to be x minus L naught. Your tension, if we solve this equation for T, it turns out then to be your delta L over L naught times your ACS times E, where this is delta L of x. And delta L of x is this expression. So here we have the relationship between tension and x. Okay? Now, I have T in here in two different ways, so I want to change my, or just amend my notation a little bit. We're going to stretch with some force T max, so how much potential energy change is there. Okay, so as a function of tension T, well, the tension function T depends on how far you've stretched it. Okay, this is how far it stretches. It's the length minus the original length, and everything goes together now. I don't want to go too far into intuitive explanation of all these things without being able to write things out. So the work done to stretch is L naught integral of the T of x from L naught to L naught plus delta L. You're just going to integrate your tension, which is the force you have to exert, the changing force you have to exert to keep stretching the wire. Okay, substituting for T of x, the expression we have here, we get this, and the integral from L naught to L naught plus delta L of x minus L naught dx, going to equal this. Antiderivative is x squared over 2 minus L naught x, simple enough. We plug in L naught and L naught plus delta L. You can verify the steps here. I tried to do this in my head. I didn't have room to write it out. And I think I saw it, but I know how it's supposed to end up, so I just did what I tell you never to do. Wrote down what I know to be the case, you know, like people do with units, wrong a lot of times. Okay, so we have this expression, which I'm not going to read to you, just this comes over here. And this evaluated between L naught and L naught plus delta L should be quantity delta L squared over 2. And again, I'm going to amend my notation slightly. We'll call this delta L max, which is the delta L at T max. And here's our final integral. Again, you can verify. And now I can write this as 1/2 K delta L max squared, where K is your force constant, equal to, well, whatever the coefficient of delta L max squared, 1/2 delta L max squared is, which is the EACS over L naught. What's that mean? It means your Young's modulus, stronger Young's modulus, a greater force constant, times your cross-sectional area, more cross-sectional area, more material to resist being stretched, and then you divide that by L naught. And there's your force constant. And this agrees with the integral you get if you simply look at this and write this as I'm going to rearrange it and rewrite it. If we write this as T equals K delta L, with K equal to this quantity, well, clearly we can do that. If you solve this for T, you've got to get E ACS over L naught times delta L. So if you define K as this quantity, this is what you get. And this is nothing but your linear restoring force. Okay. Multiply how far you stretch it by your restoring force, you get the tension. By your restoring force constant, you get the tension. So that's really what we're after here. And sorry if that's a little bit garbled with the symbols. But the point is then that if you have Young's modulus, you can write your restoring force constant as ACSE over L naught. And you get this relationship, which is the same relationship you get for a spring. Only your del L max would be your amplitude. We'll go on with the idea. Try to understand the meanings of these terms in terms of what I demonstrated with rubber bands. And just keep in mind that Young's modulus is stress divided by strain. Also has units of pressure.